Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Dear student, at the end of my first video, we have discussed the two problems associated with the root locus sketch. The discussion we did so far. In that discussion, we discussed that the value of k is necessary to find out because with the help of this value of k we would be able to find out the system response in time domain. And after the determination of this k in real practice, if we set the particular value of k that we have determined for these two search points, will automatically set the system response which we want to system must produce in terms of is its overshoot that should not exceed the required limit, which we have said earlier is about 20%, and the other time response characteristic like TR, TP, and TS, the settling time. If we have find out the controller gain and we apply the control gain in the real in the real system, in the real practice, so that would automatically set the our time response characteristics. And the second problem, how we would be able to sketch the root locus for a higher order system, because in the previous problem the problem is pertaining to a second order system, and by using the quadratic formula we are able to find out the roots of the system at different value of k in the positive side or in the negative range of the controller, and these root can be plotted on the sigma j omega plane in an easier manner, but that would not be the case for the higher order system. Okay, now here we go to address these two problems. First of all, consider the condition on magnitude and condition on angle. The purpose of condition on magnitude is to find out the value of controller gain k at a particular such point, and the purpose of condition on angle is to verify a particular such point whether or not it lies on a root locus. Okay, now let's consider the system closed loop transfer function which is equal to gs over 1 plus gshs. If we set the denominator of this transfer function equal to 0, it would be the system characteristic equation. In this characteristic equation, gshs represent the system open loop transfer function. Here is the generalized form of the open loop transfer function. K times the number of finite zeros, and in the denominator the number of finite poles. If I am separating k with the rest of the term, the rest of the term can also be written as G1s, H1s. So there are two representation of the open loop transfer function. One is with k and one is without k. If k is included, we may write the transfer function as GSHS. If k is excluded, then the open loop transfer function can be written as G1s, H1s. These are the two representation which we have used in this root locus topic. Okay, so again this is the system characteristic equation which can also be written as GSHS is equal to -1. I am separating the k terms, therefore the remaining term is G1s, H1s from this open loop transfer function, and I am applying modulos on both sides. Then k would be equal to 1 over G1s, H1s, and I am applying the value of GSHS, means the number of finite zeros in the numerator and the number of finite poles in the denominator. Then in this expression this would be like this: the poles are in numerator and the zeros are in denominator, because here I am taking the reciprocal of G1 H1s. As I have stated earlier, the purpose of condition on magnitude is to find out the value of k at a particular search point. If I am replacing this s by the search point may be real or may be complex. Therefore, if I am replacing the value of the search point, suppose s1, with this s and solving the entire term in this bracket, I would have magnitude and angle as well. Same be the case for other bracket in the numerator and in the denominator as well. So here we have consider only the magnitude information and discard the angle information. In this way we are able to find out the magnitude of k at a particular search point. Here pi is used because we have to take the product of all bracket and considering the magnitude only, and same be the case for the denominator. The n represent the number of finite pole in our given open loop transfer function, and m is the number of finite zeros, and pi represent we have to take the product of all the terms in the numerator and in the denominator of this magnitude condition. So in this way we have addressed the one problem associated with the previous video. The second one is the condition on angle. Once again consider the characteristic equation 1 plus GSHS is equal to 0. This may be write down as GSHS is equal to -1, and now apply the angle condition on both sides. If we consider the right side, here the imaginary part is 0, therefore if you take the tangent of this expression, the imaginary part is 0, then tangent inverse of 0 will come and the angle is 0, but minus sign represent the angle lies in the second quadrant. There's the angle lies in the second quadrant, then it could be written as plus minus infinity on the choice of your measurement, whether you are going clockwise or going anti-clockwise. The angle condition can be written as 2h plus 1 times 180 degree. 2h plus 1 times 180 degree. Here h is 0, here may take value 0, plus minus 1, plus minus 2. H may take any integer value. What is the physical significance is this: if you have an angle of 180 degree, if h is 0, the angle is simply 180 degree. If the value of h is 1, so it is 3 times of 180 degree, means you are measuring the same angle after its 360 degree rotation, means there is no change in the information. The second angle condition is G1 H1s is equal to 2h times of 180 degree. Once again, h may take any integer value. Angle is either 0 degree or even multiple of 180 degree. Suppose if we have this outcome like 0 degree, if the value of h is 1, this would be 360 degree, means we are measuring the same angle after a 360 degree rotation. These two condition basically is used to verify the search point whether or not the point lies on a root locus. We know that we have zeros in the numerator and poles in the denominator. If I am replacing this s by a search point once and I am going to solve this bracket, we have both the magnitude and angle information come out from this bracket. Here we have to consider the angle informations only and discard the magnitude information. If there are number of angles in the numerator, means we have to add all the angles in the we have to add all the angles of numerator, and similarly be the case for the denominator. We have to add all the poles, all the angles with respect to these poles in the denominator. If this information goes in the upper side, means the minus sign will come, because the angle can be represented as e of power j phi. If e of power j phi goes up, its sign would be changed. Therefore this sign comes from the poles angle which are going in the numerator. We may define this angle condition as if the difference of sum of angle drawn from zeros and those drawn from poles, if this outcome is equal to 180 degree or odd multiple of 180 degree, means the such point lies on RL. RL is the portion of the root locus where the controller gain is positive and its range is 0 to positive infinity. If the same outcome, the difference of the sum of poles drawn from zeros and those drawn from poles, if this outcome is equal to 0 degree or even multiple of 180 degree, means that particular point lies on CRL, and the CRL is the portion of the root locus. The point lies on CRL, and it is the portion of the root locus where gain k is where the gain k is negative. How these two conditions may be applied on any transfer function, on any open loop transfer function. So here we have to consider this open loop transfer function. It is written as GSHS, means we are including the k term with the number of poles and zeros. The given open loop transfer function has one finite zero and three finite poles. First of all, we draw the pole and zeros of G1 H1s in the S plane. We have three poles. One is at 0, the other one is at -3, and the third one is at -4. So these are the three poles, one at 0, at -3 and at -4, and 1 0 which is at -1. The cross symbol is used to represent the pole, and the circle symbol is used to represent the 0 of the system. Okay, now consider a such point. Suppose this is the point on sigma j omega plane. If we want to verify this point whether or not lies on the root locus, we have to apply the condition on angle on that particular such point. So here is the condition on angle, is the angle contribution of 0 minus the sum of angle drawn from all poles. First pole is at S, first pole is at origin, the second pole and the third pole. Next is replace the such point by the coordinate, replace S by the coordinate of the such point. I assume that the angle drawn from 0 is represented by phi, and the angles drawn from the pole are represented by theta. Therefore the mathematical expression is phi 1 minus theta 1 plus theta 2 plus theta 3. We have to solve this expression and find out the angle contribution from this pole, the angle contribution from this pole. If it is come out to be 180 degree or odd multiple of 180, means the particular such point lies on RL. If this condition fail, then we have to apply the second condition to check whether this point lies on CRL. If it is come out to be 0 degree or 180 degree, means the particular set point lies on CRL. Otherwise the S1 is not the system root or lie on the root locus. If any one condition is verified, either odd multiple of 180 degree, this one, or even multiple of 180 degree, means this one. This means this point lies on root locus, is a system root. Then we can apply the condition on magnitude in order to find out the value of gain k at that particular point. So here is the condition on magnitude. We have multiplied all the terms which are here in the denominator. The poles become zeros. The poles are in numerator and the zeros are in denominator, as we have discussed earlier. Replace the s by a search point, by the coordinate of the search point. This would give us the magnitude of k. And what would be the sign of k? Because here I am using modulus, my result is always positive. It is depending on us. Either we have to take the positive sign or the negative sign. If the condition on angle, if the condition of angle verified like this one, 180 degree or odd multiple of 180 degree, means the point is on RL. If the condition satisfied for RL, means this k should be positive. If the condition verified for CRL, means we have to take a negative value of the controller gain. At this stage, I would like to conclude the condition on magnitude and the condition on angle again. The purpose of the condition on magnitude is to find out the value of k at a particular such point, and we have to use this formula. In this formula we have to replace s by the coordinate of such point, and we have to take the product of all the terms in the numerator and the product of all the terms which are in the denominator. Therefore the symbol pi is used. If the coordinate of the such point is complex, then we have to discard the angle information and only consider the magnitude information. The value of k is depending upon whether the point is lie on RL and the point lies on CRL. If it is lies on RL, then k should be taken as positive. Otherwise, if the point lies on CRL, then the value of k would be negative. The purpose of condition on magnitude, the purpose of condition on angle is to whether the search point lies on root locus, whether it is on RL or on CRL. If the point lies on RL, then the angle contribution from all the zeros and the poles must be equal to 180 degree or odd multiple of 180 degree if the point lies on RL, where the gain k is positive. If the angle contribution from all the zeros and poles is equal to 0 degree or even multiple of 180 degree, means the point lies on CRL, where the gain k is negative. If both condition fails, whether it is not if both the condition fails, if both the condition fails, means this particular search point is not lies on root locus. Here we can say that the root locus can also be sketched by using these two conditions. The condition on angle is used to verify a search point. So we have to trial a number of such points in order to check whether it lies on a root locus or not by using equation number 9 and 10. After find out all the possible roots of the system, we are able to sketch the root locus, and using equation number 5, which is the condition on magnitude, we are able to find out the control again at a particular such point. But still we have to trial a number of such point to verify whether or not it lies on root locus or it doesn't lies on a root locus. The problem of plotting of a root locus for a higher order system is still remain, which we left in the video number 1. Okay, now let's move toward solving the second problem of sketching the root locus of higher order. There are some properties with the help of we are able to sketch the root locus of any order, either it is lower order system or a higher order system, but these properties help us to sketch the root locus in a quite easier manner. Here are some points for your understanding. Point number 1, the following properties which are going to discuss of the root loci are useful for the purpose of constructing manually and for understanding of the root loci. The properties are developed based on the relation between poles and zeros of open loop transfer function GSHS and the zeros of 1 plus GSHS is equal to 0, which is the system characteristic equation. The zeros are the roots of the characteristic equation as well. Okay, now revisiting our previous problem which we have sketched earlier by making use of quadratic formula. This is our previous problem, and we have already sketched the root locus of this system by using the quadratic formula. Here I have placed the different values of k either in the positive range, which is the range of RL, or at the entire negative range, which is the range of CRL, and we have developed the table for possible roots in case of RL and all the possible root in case of CRL. We have already done this. Now we are going to solve the same problem by using properties. Again, in this closed loop system, which is a unity feedback control system, its open loop transfer function is simply GS. Here the value of HS is 1, which is equal to K times K, which is equal to K upon S into S plus 2. If I am separating K from the open loop transfer function, then it can be written as G1. G1 is equal to 1 upon S into S plus 2. In this open loop transfer function, we have two poles. N is used to represent the number of poles. So here we have two finite poles. And what about the number of zeros in this open loop transfer function? Here M is representing the total number of finite zeros. Here the total number of finite zero is 0. This is the characteristic equation of the given system. The system is of second order because it has the highest power is 2. Now here we go. By making use of property, we are now attempting to sketch the root locus. The property number 1 is k is equal to 0 points, and we have to find out where this k is equal to 0 point lies. Again, consider the condition on magnitude. If I am placing here k is equal to 0, then the value of G1 H1 will become infinite. If I am placing in this open loop transfer function S is equal to 0, then again this G1 goes to infinity, means the K0 point lies at the poles of the open loop transfer function. So here in this case the K0 point lies on 0 and minus 2. We have already done it before when we are placing the when we have placed the value of k here 0, the both root will come out to comes out to be minus 2 and 0, and where are the pole of the open loop transfer function at 0 and -2. It means that the K0 point lies on system pole, and these are the roots of the system as well. Okay, now let's move to the second property, which is K is equal to plus minus infinity points. Again, consider the condition on magnitude. In this condition, if we place K is equal to plus infinity or minus infinity, the left hand side would become 0. So we have to find out at what value of S the left hand side would become 0. Unfortunately, in this example we have no finite 0, therefore we have to consider another example in order to understand K is equal to plus minus infinity points. In this expression, at what value of S the left hand side would become 0? Definitely when S is equal to -1, when S approaches to its zeros location. Therefore we can say that the K plus minus infinity point lies at the zeros of the open loop transfer function. Again, as I have stated earlier, in this given problem we have no finite 0, but it is the property of the rational function. It should has the same number of poles and zeros. If the number of finite poles are not equal to the number of finite zeros, then the zeros position should be at S approaching to infinity. Therefore the system has two zeros, and both zeros will be at infinity. The next property is the number of branches on the root loci. The number of branches on a root loci are equal to the degree of characteristic equation or the number of poles of the open loop transfer function. Each branch basically is the trajectory of one root, is the locus of one root, in which we have the entire range of the controller from minus infinity to positive infinity, as we have seen earlier in the root locus plot. In this root locus plot, this is the second order system. The degree of the characteristic equation is 2. The number of poles are 2. Therefore, the system has 2 branches, and each branch start from minus infinity, moves toward 0, and then finally goes to positive infinity. Similarly, be the case here. The second branch starts from minus infinity, goes to 0, and then finally proceed to plus infinity. The branch is basically, once again, is the locus of one root when K varies between minus infinity to positive infinity. So in our given problem, in our case, we have 2 poles. The degree of the characteristic equation is 2. Therefore the number of branches is equal to 2. The next property is this symmetry of the root loci. Here we have stated that the entire root locus is symmetrical with respect to real axis or with respect to the axis of symmetry. We can also see from this diagram, this root locus seems to be symmetrical with respect to the real axis. If you want to overlap this j omega axis by the lower j omega axis, then we feel that each and every point will overlap with each other. It means that the root locus is symmetrical with respect to real axis. If the roots are on real axis, these roots should definitely be symmetrical with the real axis. If the roots are complex, then the roots should be in complex conjugate form. Therefore these roots should make this symmetry with respect to the imaginary axis as well. So we can say that the entire root locus is symmetrical with respect to real axis or with respect to the axis of symmetry. We will discuss about the axis of symmetry in the next property. Property number 5 discuss the angle of asymptotes of the root loci. The behavior of the root loci at S is approaching to infinity. If the number of finite poles are not equal to number of finite zeros, then 2 into n minus m of the root loci will approach infinity. The properties of the root loci near infinity in the S plane are described by the asymptotes when S is approaching to infinity. In our case, we have two finite poles and the finite zero is 0. Therefore, the total number of asymptotes for our case is equal to 4. This property has a connection with the property number 2 and 3 as well. In property number 2, we have no definite place of the 0, and these zeros are at infinity. In property number 3, we have discussed that each branch has a start point from minus infinity and the ends point at positive infinity, or the number of branches are equal to 2 here. Therefore, for these two branches, we should know about their start point, means we have to know about where are these two negative infinity points, and we have also to find out the two finishing end of the branches, means we have to find out two positive infinity where these two branches should end. So two minus infinity points and two positive infinity points, we have to find out total 4 asymptotes in our case. We can also realize from the root locus sketch that we have done earlier. In this case, branch number 1 starts from k is equal to minus infinity, it goes to k equals to 0, and then finally it moves toward its finishing end, which is k approaching to positive infinity. The second branch has also started from minus infinity, it travels to k is equal to 0, and then finally this branch proceeds to k equals to positive infinity. If we see this example, we should know k0 point as well as we should know the k minus infinity point where the branches can started, where we are able to start the branches, and we should know about the k positive infinity point, points where the branches should be ended. So in this case, in our problem, we have only k0 points, but we do not have the information about the positive infinities. Therefore, we have to find out total 4 asymptotes. Out of 4 asymptotes, 2 basically give us information about the minus infinity points, and 2 asymptotes give us the information about the 2 positive infinity points. Property number 6, angle of asymptotes. In the previous section, we have discussed that we are needing 4 asymptotes in order to sketch our root locus. Out of these 4 asymptotes, 2 are for the starting point and 2 are for the finishing point. With the help of these asymptotes, we are able to sketch the root locus, and the system root locus on higher value of S are asymptotic with respect to the asymptotes. So we have to find out the angle of asymptotes. Theta RL is the asymptotic angle for RL only, which is equal to 2 into h plus 1 into 180 divided by n minus m, when n is not equal to m. Why? Because the asymptotes are required when n is not equal to m. Similarly, for theta CRL, the asymptotes for the starting point can be find out by using this formula of CRL, theta CRL, which is equal to 2h into 180 divided by n minus m. Here we have to place the value of h from 0, 1, 2, and the final value should be n minus m minus 1. If we apply here, in this case we have two finite poles, we have no finite 0, minus 1, this would be come out to be 1. So here h will take value of 0 and finally it goes to 1 only. We have to apply 0 and 1 in this formula of theta RL in order to find out the finishing end of each branch, and we have to apply h0 and 1 in this formula in order to find out the starting point of each branch. By placing these two values, the theta RL comes out to be 90 degree and 270 degree, and theta CRL comes out to be 0 and 180 degree. The another question is from where we have to plot these angles. This angle will be plotted by using the next property, which is the intersection of asymptotes or centroid. From here we also find out the axis of symmetry as well. Sigma is the real part, is the real value, which is equal to sum of poles minus sum of zeros divided by n minus m, and this will give you a real value where all the asymptotes will intersect each other. So here we go. Sigma is equal to one pole is at 0, the another pole is minus 2 is the sum of pole minus the sum of 0, we have no 0 here, divided by n minus m, 2 minus 0, therefore sigma comes out to be minus 1. This minus 1 is the point where we have to plot these four angles for four asymptotes. Next property is the property number 8, the root locus on the real axis, which is stated that the entire real axis is occupied by the complete root loci, either by RL or CRL, which means that the entire real axis represents the system root, whether it is occupied RL or it is occupied by CRL. How we are able to determine which part of the real axis is representing CRL and which part is representing CRL, for which there is a mechanism or there is a use of condition on angle, by which we are able to find out the portion of the CRL and the portion of the RL on the real axis. Okay, now let's move to sketch the root locus with the help of properties we have discussed so far. Is the sigma j omega plane. First of all, we have to apply the property number 1. The property number 1 is k is equal to 0 points, and this k 0 points are at 0 and minus 2. So use cross point for representing the system pole. Here the value of S is 0, as well as the controller gain is also 0. The second pole is at minus 2. Cross is used to represent the system pole. Here the value of S is minus 2, the sigma is equal to minus 2, and the value of the controller gain is also 0. Now I am going to save this image for further use. Okay, now comes to the property number 2. In property number 2, k which discuss the k is equal to plus minus infinity point, and these points are at system 0, and we have no finite 0 in our case. Therefore we could not be able to place the finite zeros in our sketch. The proper number 3 is the number of branches on the root loci. In this case, we have 2 poles. The degree of the characteristic equation is 2. Therefore, we have 2 branches. This property also says that each branch has a start point from where k is approaching to minus infinity, and from this minus infinity point, from this k is equal to minus infinity, the branch is traversing and reach to k 0 point, and then finally proceed to positive infinity point. So we have to show in our sketch the start point of each branch. If the number of branches are 2, means we have to represent 2 minus infinity point in our sketch, and we have to represent 2 positive infinity point in our sketch, as we have already show the k0 point for these 2 branches. So how the positive and negative infinity points can be marked? These 2 points, this positive and infinity can be marked by the with the help of asymptotic angle. The asymptotic angle, the asymptotes angle for theta RL is 90 and 270 degree, and the angle for the CRL, the angle of asymptotes for CRL is 0 degree and 180 degree, and we have to plot these 2 angles with the help of property number 7, which give us the intersection of the asymptote which is at -1. Okay, let's go. At -1 we have to plot asymptotic angle. The asymptotic angle for RL is 90 degree, is the point where the branch comes to an end, and the other one angle is 270 degree, is the angle for RL. The angle for CRL with respect to this centroid is 0 degree and 180 degree. So 0 degree is here. So I have to mark here k minus infinity. And the second angle for the second asymptote angle for the CRL is 180 degree. So is the 180 degree, is the angle of 180 degree. So the second branch have a start from here. Now in our sigma j omega plane, we have 2 minus infinities. These are the 2 starting point, and 2 k0 point where the branches from here arrives to k0, and 2 positive infinity where these 2 branches proceed to their endpoints. Once again, I have to save this image for further use. Okay. The property number 8 says the entire root locus is occupied by the complete root loci, either by the CRL or either by RL. So we have to identify which portion is representing CRL and which portion is representing RL. Here we have to apply the condition on angle. Once again, first of all, I have to find out whether this portion belongs to CRL or RL. The method is, first of all, take a search point here. Suppose this one is the search point, And with this search point, with respect to search point, count number of pole and zeros in the right side of the search point. If the count comes out to be 0 or even number, means the particular search point is on CRL. If the count comes out to be odd number 1, 3, 5, means that particular point is on RL. Okay, now let's go to count the number of poles and zeros in the right side of the search point. So what about the number of pole and zeros here? The count is 0, means this search point is on CRL. With respect to all these search points, the count on the right side is 0. Okay, up to this pole, my count remains 0, means this portion represents CRL. Okay, this particular color is used for CRL. Then after this pole, my count is 1. If I am counting with respect to this search point on the right side, the number of pole and zeros, if my count comes to be odd number, means this particular point is on RL. My count is 1, my count is still 1, my count is still 1, still 1, still 1, means these all points which are representing the system roots lies on RL. Beyond that, once again my count is 2, means all these points belongs to CRL. So in this root locus, we have the distribution on the root locus, where is CRL and where is RL. We have also the starting point of each branches, the intermediate point of each branch, and the finishing end of each branches. From here the branches are from here the branch should have a starting point. Therefore I am using the inverted arrow in both sides, and here the branch has the end point. Therefore I am using the outward arrow. Okay, now consider the branch number 1. The branch number 1 has a start point from k minus infinity. It is proceeding on the real axis, because the real axis has CRL here, and the CRL has the range of k from minus infinity to 0. It is the range of CRL. So the branch starts from k minus infinity and approaching to 0. The second branch which belongs to CRL starts from k minus infinity, and this branch is proceeding along the real axis, because this portion of the real axis belongs to CRL, and this branch arrives to k0. So we have completed 2 CRL. The two branches and their pertaining CRL portion. Next, these two branches moves on RL. So this should be the direction of this branch, comes from minus infinity, and then further proceeding in this direction. This branch comes from minus infinity, approach to 0, k0, and further this branch moves to we will move in this particular direction. Here we can see that there will be a point between s is equal to 0 to minus 2. From s is 0 to minus 2, where these two branches should meet each other and then depart for their endpoints. So we have to find out a quantitative value of the point where these two branches should meet and then depart to their positive for their positive infinities. Once again, I should save this image for future use. As I have said earlier, these two branches, when moving along RL, the range of the RL is from k greater than equal to 0 and less than positive infinity. Here is also less than and equal to 0. So when these two branches are moving along the real axis from k0, they should meet at some point where the value of k is maximum. The value of k is maximum with respect to the existing values of k along this particular portion, and then these two branches depart for their positive end. So we have to find out the maximum value of k on this particular portion with respect to the existing value of k. I have to save again this figure for next use. Okay, so the maximum value can be find out by using another property, which is the breakaway point, which discuss the breakaway point. In this property, the breakaway point on the root loci correspond to multiple order root of the equation. It is also obvious from this diagram. One branch is moving in this direction and the another branch is moving in this direction, and both branch will meet at some point. This point correspond to number of root with respect to the number of branches involved in the breakaway point. So here two branches are involving in breakaway point, means when they meet, the meeting point correspond to two roots of the system. The roots will be real and equal according to the situation is given here. So breakaway point on the root loci correspond to multiple order root of the equation. The breakaway point the breakaway or break-in point occurs where the gain k is maximum and minimum respectively. The breakaway point occur where the gain k is maximum, and the break-in point is occur where the gain k is minimum with respect to the existing values of k on that particular portion. How we can find out the maximum or minimum value? We can do so by differentiating the characteristic equation after formulating like this: k is equal to -1 over g1s h1s, and differentiating this equation with respect to s in order to find out the maximum and minimum value of k, and after differentiation equating the derivative is equal to 0. After simplification, we can easily find out this expression in a simpler manner will be equal to d by ds of g1s h1s is equal to 0. The inside the square bracket we have already known is the open loop transfer function, is the system open loop transfer function without k. So here we have implemented the same thing here. We have differentiated the g1 h1s of the given system, differentiated with respect to s, and after solving we have found that the real value, the solution of the s is equal to 1, which means that both the branches will meet at s is equal to -1. Okay, again consider this figure. these two branches will meet at this point and then will depart. So what would be the angle of departure? If these two branches depart, then which angle they follow? This angle can be find out by using this formula. The angle of departure would be equal to 180 divided by n, where n is the number of branches involved in the departure. So here two branches are involved for the departure. Therefore, if we use this formula, 180 divided by 2 means the angle of departure should be 90 degree. Same be the case for another branch, because if the roots are complex, then these root will be would be in the complex conjugate form. So due to symmetry, the angle should be minus 90 here. So this branch after departure will go to its positive infinity here, and this branch will go to its respective positive infinity here. So in this way we are able to sketch the root locus. I am again saving here for any further use in the future. Look at here is the root locus plot. The range of the branch, the range of for each branch is from minus infinity to 0 is the range for one branch, and the range of for one branch is again minus infinity to 0 and 0 to positive infinity. These two branch has a breakaway point at s is equal to minus 1 that we have found earlier. S is equal to minus 1 is the point where these two branch meets and depart. And what would be the angle for the departure can be calculated by using this formula. Okay, here are some important points regarding the solution of this equation star. All real solution of equation star, all real solution of equation star, all real solution of real solution of equation star are the breakaway points on the root loci, since the entire real axis is occupied by the root loci. Means if the solution of this equation are real, means that would lie on the real axis, and the entire real axis shows the system root, then we have to accommodate the solution of this equation into our root locus sketch. We cannot discard the solution of equation star if it come out to be real. In case of complex solution, they may be or may not be the breakaway point. They are the breakaway point only if they satisfy the characteristic equation. We have to place the value of s in this expression. If the value of a comes out to be a real one, means the complex solution would also be the breakaway point. If after placing the solution of equation star in this characteristic equation, if k comes out to be complex, then we have to discard that solution, because the controller gain cannot be complex. It is not possible to have a controller gain in complex form. So the controller gain should be a real one. After finding the breakaway point, we can also find out the value of k at the breakaway point. Consider here again the condition on magnitude. in our case we have two poles, s and s plus 2. These two terms are here in the numerator, and we have no 0 here, so I have write down here 1 here, because in our equation we have already write down 1 in the numerator, so we have 1 here. Further replace s by the solution of equation star, which is -1, which give us the value of the controller, which is also comes out to be 1. It is not necessary that k always come out to be 1 when we placing 1 here. It may be any value, but what would be the sign of this value? For this we have to check our root locus where this point lies. If this point lies on RL, then k should be taken as positive. If the point lies on CRL, then the value of k would be negative. The value of k can also be find out by using the system characteristic equation. This is the system characteristic equation. Under the square bracket is the open loop transfer function. If you replace s by the solution of the equation star, which is -1, if I am placing here -1, then again k comes out to be 1, because the magnitude condition is also derived by using the system characteristic equation. Therefore, either by using this magnitude condition or by using the system characteristic equation, we have the same answer for the controller gain. So finally, in this way, we have plotted the second order system in which we have two branches. Each branch has a start point from -infinity. The branch goes to k0 and finally proceed to k positive infinity. The second branch has the similar trajectory, start from -infinity, it covers its k0 and then finally goes to positive infinity. This is all from video number 2. Thank you very much for being here with me. Allah Hafiz.